So this talk is about the performance of internet protocols and satellite communication. It actually does not include mobility. We have had a lot of talks about this. So we are currently focused on stationary internet access, but consider this kind of an upper bound, because once your user terminals are moving, things do not get easier. So here's the outline. Let's start with a very brief recap of the different satellite communication technologies. So there has been the question before, what's the capacity of a spot beam? I was fool enough to put some numbers on my slides. One of the recent satellites is the Connect Very High Throughput satellite, which has a total capacity of 500 gigabit per second. And as a rough number, consider 50 spot beams. So if you divide 500 gigabit per second by 50, you end up with 10 gigabit per spot beam, just as a rough number. Has been around for some time, works, we all have heard it, the high latency is problematic. More recently, Starlink has been available. So the monthly costs vary. In Germany, they have been reduced to 65 euros per month. In some parts of the US, you have to pay $120. Some performance figures from a crowdsourced website. So basically, Starlink users put some Raspberry Pi or some computer into the network and just run regular speed tests. And the numbers we see are in the download direction in the European Union, roughly 200 megabit per second, while we have lower numbers in the US, roughly 130 megabit per second. So this already indicates that the subscriber rate in the US is much larger than in Europe. Okay, let's have a look at how do the different technologies compare. So on the left side we have Starlink, on the right side we have a geostationary satellite, and we will look at how fast is a website being loaded. And it's typical for the geo system that initially you have some kind of delay until the first content comes in. And once the content comes in, it's quite fast. But you see that the lower latency of the LEO system is really beneficial for loading a website. Another example is accessing some files via Samba share. On the left side we again have Starlink, and we are just clicking through the folders, and you see it's quite smooth. On the left side it works like you would expected. Whereas on the right side, the GeoSatellite, you have some annoying delays, let's say, and that's just one of the drawbacks for applications and protocols of this high latency link. Okay, so this is the last talk for today, and some of you may already be hungry for lunch, but let's dive into the fundamentals of internet protocols. So the internet in a nutshell. On the lower layers we have the communication between 2 points, so really the transmission of zeros and ones. Like for me as a computer scientist, this is the less interesting part, but I know that there are a lot of experts here for this part. Then we have the network layer, which basically we have packet switch networks, so the network layer gives you a path through the network. This is how your packets are traversing the network. And our focus is the transport layer, where we abstract from the path of the precise path of the network just to an end-to-end connection. So we put stuff into the network and we receive it, and then we have just this abstract logical communication channel. And then of course on top we have the application. Now if we consider loading a website, there are many protocols involved. So we start with a DNS request to get the IP address of our URL. Then we have to do a TCP handshake. Then we probably want to have encryption, so we need a transport layer security handshake. Then we need to send a request for the base page. Once we have received the request for the base page, we need to request the embedded objects, and then we have a thing which is called slow start. So the sender does not send you the complete object at once. Instead, it sends a few packets, it waits for an acknowledgement, it sends more packets, waits for an acknowledgement, and so on. This is called slow start, and like the challenge for transport layer protocol is really to adapt to the path which we do not know in advance. So path characteristics can change, either because of the underlying transmission channel, especially if it's wireless, it's not stable, it's fluctuating, or also because we have different applications running, or maybe we have multiple computers sharing the same bottleneck link. And the challenge for a congestion control algorithm is like, imagine getting into a car, blindfolded and deaf, and trying to figure out how fast you can go. That's the challenge for a transport layer for congestion control algorithm. So we need to adapt to the bottleneck link capacity, and we have to provide fairness if there are multiple flows. How is this realized? So widely deployed algorithms are so-called loss-based algorithms, which means we again have the slow start. So we start to stand slowly and get faster and faster. So the buffers fill up, and once they're full, we have packet drops, and these packet losses are an indication for that we have sent it too fast. So we throttle the sending rate, and then we again increase the sending rate because the path characteristics might have changed, until we again see losses, and then we reduce the sending rate, we increase it, and so on and so on. This is actually not optimal because it first fills the buffers. What would be better are so-called delay-based congestion control algorithms, which provide lower latency because they see that buffers are getting filled, and then the latency increases, so they throttle their sending rate much earlier. And the only problem is that nowadays deployed algorithms are loss-based, and they have a certain aggressiveness, and so a delay-based algorithm cannot compete with those loss-based algorithms because they are not aggressive enough. So basically the loss-based algorithms will steal the whole capacity from a delay-based algorithm. And there's a side effect which you can observe by having large buffers. So this is the Starlink system. We're sending some packets to a server. You see latencies, round trip times, roughly 30 milliseconds. And then we start some cross traffic. So we start some additional TCP traffic. And once this happens, you can see that the latency goes up at almost two times, up to 160 milliseconds. So once you put load onto your bottleneck link, the latency increases. This is of course not optimal. Okay, so geostationary satellite, we have this high delay, and this is challenging for protocols because the feedback loop between sending a packet and receiving a packet is very long. And you also have to send really a lot of data for these numbers here, 7.5 megabyte, to really fill the pipe. And if you have some packet loss, it takes you a long time, like 600 milliseconds, to recognize the packet loss and to retransmit the packet. And within this time frame, your path characteristics might have changed completely. So what is being done? So-called TCP proxies, which split the TCP connections into multiple control loops. So then you can do the slow start much faster, and you can also do retransmissions much faster. Unfortunately, this does not work for TCP when headers are encrypted. So if you have a VPN, or if you have this new transport protocol called QUIC, which we will talk about in a second, this does not work. Such TCP proxies are also considered one of the root cause for ossification. In German it's Verknöcherung. Also, which is simply that you cannot change TCP anymore. TCP is as it is. Changing TCP does not work because middle boxes will not be able to handle any changes. Here are some performance results. So we see again a geostationary satellite. The blue line is with PEPs enabled, so you see a very quick ramp up to your link capacity of 50 megabit per second. And once you have a VPN, which is the orange line, you can see that you don't reach the capacity at all, and it really takes you a very long time to get up to speed. For the VPN case, it also matters which kind of congestion control algorithm you're using. Compare this with Starlink. First of all, you have higher numbers. And you see, so Starlink does not have these performance enhancing proxies because of the low latencies. So you can see that it does not matter if you have a VPN or not. What matters more for Starlink is the type of congestion control algorithm. So here BBR is the delay-based algorithm, works better than Cubic, which is a loss-based algorithm. Okay, what are concrete transport protocols? We have UDP, which is very simplified. It only provides a checksum. It does not provide flow or congestion control at all. Then we have TCP, which is more complex. We have a reliable protocol, so we have sequence numbers and we have acknowledgements. And the interesting thing about TCP is it has been standardized in the 80s, and it's still around. So considering communication systems, 40 years is quite a lot, and we're still using TCP today. Of course, with a lot of minor modifications, let's say. But the key concept is still is very old. So this is one motivation for a new transport protocol, which is called QUIC. QUIC does not have one single header. The headers in QUIC are quite versatile and different. So QUIC provides a lot of features which you want to have from a modern transport protocol, including a fast connection setup, encryption by design, and it's extensible and it's evolvable. So QUIC contains a lot of features like security and congestion control combined in one layer, so this could be considered some cross-layer optimization. Interestingly, it has already been deployed by Google since 2013. So Google said, okay, we want to have a better transport protocol. And because Google controls a lot of servers and also a lot of clients by their browser and by Android smartphones, they simply deployed it. So they played around with it before it has been standardized. And this is typical for the IETF, where internet protocols are being standardized. They believe in a slogan called running code. So they first want to see how does it behave in the wild, in real, and then they standardize it afterwards. So QUIC has just been standardized, I guess, last year. Okay. Finally, multipath communication, we have also touched this topic before. So devices nowadays have multiple network interfaces, also cars. So you want to use satellite communication, but you also want to use cellular communication. So multipath communication provides you seamless mobility. It increases your reliability and performance. There are some specific protocols to achieve multipath communication, and it's also part of 5G called access traffic steering, switching, and splitting, where traffic steering is like selecting the best path for a new flow. Switching is switching one flow from one path to another path, and splitting is like simultaneously using multiple paths. So Splitting is like you have two 10 megabit interfaces and you end up with 20 megabit flow. In general, the more heterogeneous the paths are, the more difficult multipath communication is, and which is a short advertisement for a previous project which we have done, where the task was to combine slow DSL lines, like DSL Lite, with some geostationary satellite internet access, where both the data rate and the latency are an order of magnitude different. So this is interesting from a research point of view. We have achieved some good results with that approach, I would say. It is based on PEPs, so this is kind of problematic, but I won't go into details for this approach here. Okay, some trends in satellite communication and computer networking. Most of this we have heard already before. More mega constellations, 5G and non-terrestrial networks. Of course, also the protocol performance plays an important role in these systems. We have heard AST Space Mobile a few times before today, and we have satellite IoT, which also which can be used already today. Some trends and challenges in computer networking. So quality of service is not a new concept, it's like self-evident in the meantime. But instead of going into details, I would simply like to ask you, in the few years you had a lot of video conferences, and how often have you been in video conferences and thought, oh man, the audio and video quality is really poor. So just think about this and think about, does quality of service really work today in all fields of in all applications? One general trend which can be observed is that latency is more important than throughput. We have seen this with the buffering effect. So for many applications, the responsiveness, the latency is really, you do not gain a lot by switching from 200 to 300 megabit, but you gain a lot by cutting down the latency a few milliseconds. A lot of new concepts and architectures exist. So from Academica presents new concepts frequently. One of the challenges in the internet is simply the deployability, because you cannot change every device or every protocol stack of every device. So this is really a key problem. More specifically, satellite networks. So we see a rise of encrypted traffic, which is especially problematic for geostationary satellite networks. Here, QUIC is both a problem because PEPs cannot be applied, but it's also a chance because it contains a lot of features which are really desirable. For Starlink, we see high data rates, low latency, but also varying data rates. So with Starlink, we see data rates jumping from 0 to 200 megabit within a few seconds. Yeah, so it's really not very stable at the moment. Let's see if this is going to be improved. And we also see quite a lot of packet loss, like in the range of 1%, which is a lot for the protocols we're talking about. And we have the integration of satellite communication into vehicle networks, which already Helmut did give a great presentation. Okay, this is my summary. So geostationary satellites work, mega constellation, Starlink. The performance is really impressive, I would say, for a lot of protocols and applications. There are further innovations ahead, and it's like there's a lot of stuff going on in satellite communication, and there's also a lot of stuff going on in protocol development, which makes it very exciting to do research in this field. Because we have QUIC, we have new congestion control algorithms, and we have multipath communication. So that's it from my side. Thank you.